In this learning objective, we will see how assembly is translated into machine's language, zeros and one. We are now ready to explain the difference between the way humans' instructions are interpreted by the computer and the way that computer sees the instructions. Everything we learned so far in assembly, um, S1, S2, add, subtract, LW, T0, all of them should be translated to numbers, binary numbers. This is what hardware understands. For example, S0 is coded as 16 or 10000 in binary, and that's what machine would understand. Let's see how we get to translate MIPS assembly instructions. Human sees assembly, for example, add T0, S1, and S2. Machine sees the same instruction in numbers. Instruction is encoded into a particular format, multiple fields. Each segment is called a field. For example, add is encoded into 6 number fields. Every field has a particular meaning or hint for machine to know what is the instruction. First field from the left tells this is an ALU instruction. Second field says the first operand should be collected from S1. Third field says the second operand should be collected from S2. Fourth field says the results should be stored in T0. Fifth field is not used in this instruction. Sixth field says the operation of ALU is add. And these all are read by machine and understood, just like the way humans look at the braille writing and grasp it. To be more accurate, machine understands zeros and one only. So for us to get to zeros and one, we follow 2 steps. We convert the instruction into decimal fields, then we convert the decimal values into binary. This layout of n numbers of field is called instruction format. All MIPS instructions are 32-bit. In this example, 1 6-bit, 5-bit, 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 and the last 6-bit, total of 32-bit from 6 different fields. Some other instruction set might have variable instruction sizes, but MIPS follows the design principle, simplicity favors regularity, and have one single instruction size, 32-bit. Strictly speaking, machine language is the binary representation of an assembly instruction. And machine code is the sequence of binary instructions. For simplicity, we represent machine code using hex or base 16. Every hex number corresponds to a 4-bit binary number. Table here shows the binary equivalent of every hexadecimal number. This example here show how we can convert hex number to decimal, hex number to binary, and from binary back to hex. Here we see how we can convert a 80-digit hex into 32-bit binary and vice versa. This conversion can all be done by looking up the table we saw in previous slide. So let's have a look at the fields of MIPS instructions and understand the meaning of every one of the fields. OP is a basic operation of the instruction, and traditionally this is called opcode. RS specifies the first register source operand. RT specifies the second register source operand, and RD specifies the register destination operand. It's where the results of the operation will be stored. SHAMT is the shift amount. It's only used for shift instructions. And the last field, funct, is a function. This field, often called function code, selects the specific variant of the operation in the OP field. For instance, OP specifies all the data transfers, function specifies which specific type of transfer, bytes load or word store whatsoever. Now is a good time to call the third design principle. Good design demands good compromises. A trade-off that MIPS takes is to keep all instructions same length, but have different instruction formats. For example, we have R-type format with 6 fields to use for add, subtract, and or generally any 3-register operand arithmetic logical operation. And we have another format called I-type format with 4 fields only. And that is being used for instructions that have 1 immediate and 2 registers as operands. Examples of I-type instructions are add I or add immediate, and all the data transfer instructions we seen earlier. Instruction formats are distinguished by the OP field. OP field is common between all types of instructions. Machine reads this field from the 32-bit of the instruction word, and then figures out what is the instruction format, and then based on that, reads the remaining field. If it's I-type, reads 4 fields. If it's R-type, it reads 6 fields. Let's translate a C code all the way down to the machine language, zeros and ones. Assume the C code is already translated to assembly sequence given in this slide. Now our task is to convert every single assembly instruction to machine binary sequence of 32-bit instruction words. We accomplish this in 3 steps. For every instruction, we complete 3 steps. First step, we find the instruction format. Is it R-type or I-type? Then we find the value for every one of the fields in decimal. And finally, we convert the decimal to binary. Let's start with the first instruction. Step 1, finding the instruction format. We find the instruction format by looking at the MIPS reference data manual. It is a 2-sheet document that lists all the code for all assembly instructions, mnemonic registers, and everything we need for generating machine binary. First column of the first sheet lists the instructions formats of all instructions. Find the row that the instruction is at and find the column under format. The intersection there indicates the format. If it's I, it indicates the instruction is I-type. If it's R, that indicates instruction is R-type. For LW instruction that we are looking at, instruction format is I-type. The number of fields in I-type instruction can be looked up on the same sheet at the bottom left. As you can see here, there are 3 different formats in total in MIPS. LW instruction, we found that it's I-type, so the number of fields we are looking for are 4 fields. Now let's find the values of all fields. We look at the same column that we found the instruction format first. To find the opcode, look at the opcode column. Here, the opcode is 23 in hex. That is 35 in decimal, and that's our opcode. Immediate value is the offset we see in the instruction itself, 1200, and that's the value of immediate in the instruction. Looking at the operation column, we see that the RT defines the register that the ultimate result will be written to. Looking at the instruction itself, we know that T0 is the register that is going to be written. So the value of RT should be T0. So we take a note of that in the instruction. And the value of RS should be T1. That's the only unused register in the instruction that will replace RS. Now we need to convert T0 and T1 to numbers. We look at the table on the right bottom of the reference datasheet. There is a table that lists the code for all registers in MIPS. T0 and T1 are 8 to 50. So we can conclude T0 is 8 and T1 is 9. So that gets us the entire decimal for every one of the fields. Table here lists the decimal values for all other instructions. Every row in the table lists machine code of one instruction. The last step is to convert every decimal value to binary. Here are the converted values and final machine binary. Sometimes we want to generate the assembly code from machine binary. That's inverse of what we did so far. This process is called disassembly. By looking at OP and function pair values and confirming from MIPS reference data, we know that this is a subtract instruction. So option 2 can be eliminated because that's add instruction. From instruction format, RD is where the result is stored. RD in the instruction word is set to 10. Again, from MIPS reference data, we can find that 10 belongs to register T2. T0 is 8, T1 is 9, so T2 is 10. So option 1 will be eliminated because destination is not T2 in this instruction. In the instruction word, we see that RS is 8 and RT is 9. This means that first operand is T0 and second operand is T1. So the correct answer is option